For thousands of years, this strait has been a place of conflict. Why?
This map tracks the pulse of global energy. Every day, roughly 1/5 of the world's petroleum and a massive portion of liquefied natural gas pass through this single gap. At its narrowest point, the Strait of Hormuz is just 2 miles wide. لطفاً کانال ما را سابسکرایب کنید. این ویدیو را لایک کنید و نظرات خود را برای ما بنویسید. This is the Arleigh Burke-class destroyer, a vessel designed for operations in such high-tension environments. Surviving a choke point like this requires more than just raw firepower. To keep these waters open, the U.S. Navy relies on a platform that combines structural resilience with the ability to strike targets from hundreds of miles away. Navigating a 2-mile-wide corridor surrounded by hostile coastlines creates a tactical trap known as anti-access area denial, or A2AD. In the open ocean, a ship has time to detect a threat. Inside the strait, the geography eliminates almost all reaction time. The littoral or coastal waters are saturated with asymmetric threats. Radar operators must simultaneously track fast attack craft and anti-ship cruise missiles launched from hidden mobile batteries just over the horizon. In these confined waters, even basic unguided artillery or small boat swarms pose a risk to a multi-billion-dollar surface combatant. A single successful strike here can trigger a global economic disruption. Securing this passage requires a ship explicitly engineered to absorb littoral damage, process multiple threats in seconds, and execute strikes without needing to enter the narrowest parts of the Persian Gulf. Because coastal combat increases the likelihood of taking a hit, the Arleigh Burke-class is built entirely from steel. This avoids the risk found in older warships that used aluminum topsides, which can suffer catastrophic melting in high-temperature fires. Beneath the steel, the ship's vital spaces are further protected. This cross-section shows the Combat Direction Center and missile magazines, shielded with Kevlar armor against fragmentation. To handle volatile zones, the ships use a countermeasure washdown and central atmosphere monitoring system, creating a protected internal environment against CBR contamination. These engineering choices ensure the ship remains a viable combat platform, even after sustaining damage that would neutralize a less resilient vessel. The destroyer's situational awareness comes from the AN-SP1 radar. Unlike traditional rotating dishes that see a patch of sky every few seconds, these 4 static faces send out energy beams across 360 degrees constantly. This unblinking eye can track over 100 targets simultaneously, ranging from sea-skimming cruise missiles to high-altitude ballistic missiles passing through the upper atmosphere. In the electronic warfare environment of the Middle East, the SP1 can concentrate its energy into a high-powered focus. This allows the ship to burn through enemy radar jamming attempts, ensuring the tactical picture remains clear. This chart shows the automated defensive layers managed by Aegis. The outer shield uses SM-3 and SM-6 missiles for high-altitude threats. The inner shield utilizes SM-2s for medium-range intercepts. Finally, the close-in shield uses Sea Sparrow missiles and phalanx guns against fast attack threats. By managing these defensive bubbles automatically, the Aegis system allows the crew to coordinate complex offensive strikes, while the ship maintains its own protection against incoming saturation attacks. The ship's primary offensive power is housed in the Mark 41 vertical launch system. It replaces slow mechanical reload rails with a subterranean honeycomb structure built directly into the deck. This layout features 96 total cells. Because every missile is ready to fire, the ship can switch from air defense interceptors to offensive Tomahawks in seconds. There is no mechanical delay waiting for a launcher to reload. This system allows the Arleigh Burke to ripple-fire massive volleys of missiles. By launching dozens of Tomahawks in rapid succession, the destroyer can overwhelm even heavily fortified coastal command structures. Because the entire payload sits flush with the deck, the ship maintains a lower radar cross-section than older warships. This reduces its detectability while maintaining the capacity for a massive offensive strike. This range is what changes the geometry of the battlefield. Advanced Tomahawk cruise missiles can reach targets over 1,000 miles away. This allows the Navy to strike critical infrastructure near the strait without ever sailing into the reach of coastal artillery. Positioning ships in the Arabian Sea provides a defensive buffer south of Oman. This cushion gives the Aegis system minutes, rather than seconds, to detect and destroy any threats launched from the coast toward the fleet. the reach is so significant that ships in the eastern Mediterranean can strike targets near the Gulf by routing missiles over land corridors. This allows for offensive operations from entirely different bodies of water. Modern naval operations and chokepoints rely on this standoff capability. By using weapon range to move the fight into open water, the Navy systematically dismantles coastal defenses from a position of relative safety. In the opening hours of a major escalation, manned aircraft and carriers are often held back. Flying multi-million-dollar jets into a fully alert, integrated air defense network carries a high degree of risk for the pilots and the fleet. Instead, the Arleigh Burke destroyers act as the door kickers. They launch the initial unmanned Tomahawk volleys necessary to blind the enemy's coastal radar network and neutralize their missile batteries. The synergy of the Arleigh Burke and the Aegis system is what maintains the deterrent. By extending the reach of their weapons and the strength of their shields, these destroyers ensure that any attempt to close a global chokepoint begins with the systematic dismantling of the adversary's own defenses. Imagine a machine hurtling through a narrow mountain canyon at nearly 600 miles per hour, completely empty of human crew. As it flies, it is rapidly sweeping the earth below it with a radar pulse, generating a live, three-dimensional topographic map to find its way to a single hidden doorway carved into a rock face. This sequence describes the standard flight profile of the Tomahawk land attack missile. For decades, naval commanders faced a brutal math problem. Taking out heavily fortified coastal targets meant sending pilots directly into dense integrated air defense systems, tightly woven networks of surface-to-air missiles and coastal radars, where the risk of losing multi-million-dollar aircraft and the humans flying them was incredibly high. The solution was standoff warfare. This tactical doctrine allows a military force to strike high-value targets from hundreds of miles away, well outside the lethal range of those coastal defenses. We see automated 3D scanning tech in commercial drones today, but I'm curious to know what you think. Could modern civilian scanners ever match this level of military precision? Let me know in the comments below, and hit subscribe while you're there. By utilizing a highly advanced robotic brain to navigate rather than a pilot, the Tomahawk acts as the United States Navy's razor-sharp spearhead, absorbing all the physical risk while delivering near-metric precision. When a Tomahawk strike begins, the missile is at a dead stop inside the vertical launch system of an Arleigh Burke-class destroyer. To reach flying speed from zero, the missile is violently expelled from its canister by a solid propellant rocket booster. Within seconds, it clears the ship's deck and reaches the necessary velocity for sustained flight. Once the initial thrust is complete, the solid rocket booster burns out and drops away. The missile's cruise wings deploy, a belly inlet opens, and a miniature, highly efficient turbofan engine ignites, running on high-density liquid JP-10 jet fuel. Now in its cruise phase, it travels at a high subsonic speed of roughly Mach 0.74. Its sleek shape, combined with specialized radar-absorbing materials, gives it a remarkably low radar cross-section, making it exceptionally difficult for ground-based early warning systems to spot. This two-stage mechanical sequence converts a static, heavy cylinder into an agile, stealthy, jet-powered aircraft in less than a minute. But physical stealth is only half the equation. The real challenge is navigating over 1,000 miles of trackless oceans and complex geography without a single steering input from a human operator. To do this, modern variants rely on three distinct, overlapping layers of guidance. Layer 1, an inertial navigation system paired with military-grade anti-jam GPS. Using sensitive gyroscopes and accelerometers, it calculates exact speed and direction, acting as a highly precise internal compass and clock. If GPS signals are jammed by an adversary, the Tomahawk seamlessly shifts to Layer 2, terrain contour matching, known as TERCOM. This diagram shows how TERCOM operates. A radar continuously shoots pulses downward to measure the distance to the ground, capturing every valley. The computer compares this real-time data against preloaded 3D maps in its memory, finding a match to immediately correct any flight path drift. TERCOM effectively turns the Tomahawk into an autonomous geological scanner. With varied terrain below it, the missile always knows precisely where it is. However, as the missile nears its final destination, general navigation is no longer sufficient. Striking the general vicinity of a target is useless if the objective is a specific ventilation shaft or a single bunker door. This is where the final guidance layer engages. Digital Scene Matching Area Correlation, or DSMAC. This split-screen simulation illustrates how it works. An optical camera beneath the nose takes high-resolution photographs of the target zone. The computer compares these images pixel by pixel against stored satellite photography, actively searching for structural edges to lock onto the precise impact point. By stacking GPS, radar topography, and optical scene matching, the missile's brain shrinks its margin of error down to less than 10 feet. To see how this hardware operates in a high-stakes environment, look at the narrow, heavily monitored waters of the Strait of Hormuz. Here, land-based coastal missile batteries can hold global shipping routes hostage from the shoreline. If a Tomahawk is launched from the Arabian Sea, flying in a straight line over open water would make it highly visible. Instead, the missile is programmed to immediately cross the coastline and enter the rugged valleys of the Zagros and Al-Hajar mountain ranges. It utilizes a tactic known as terrain masking. Dropping to altitudes as low as 100 feet in a terrain-following flight profile, the missile physically hides behind rock ridges and valley walls. The surrounding granite absorbs and blocks the radar waves emitted by coastal defense systems, keeping the missile hidden until it pops up over the final ridge. Instead of treating the Earth's toughest geography as an obstacle, the missile uses the landscape itself as a physical cloaking device. Modern Block 4 and Block V Tomahawks operate as fully networked assets, maintaining constant communication with off-board platforms throughout their flight. Thanks to a two-way satellite data link, they possess a loitering capability. The missile can fly in holding circles over a safe patch of ocean for hours, waiting for real-time intelligence to confirm an enemy radar has turned on before initiating its dive. If a mobile launcher moves, operators can send new coordinates to the missile mid-flight. And just before impact, the Tomahawk can transmit a single high-resolution battle damage assessment photo back to the fleet, confirming the strike for the commanders. The fusion of jet propulsion with live 3D ground scanning is a remarkable piece of engineering. Let me know down in the comments which part of the Tomahawk's navigation system you find most impressive. By relying on pure technological precision and extreme low-altitude flight, this system removes the guesswork from naval strategy. It ensures that even the most heavily fortified coastlines can be neutralized from a distance, providing a quiet, absolute shield over the world's most critical maritime corridors.